Okay, question 9. A learner conducts an experiment. Learners conduct an experiment as shown in the diagram below. And so there's the experiment. The results are obtained in the following graph. So they are plotting the potential difference and the current on the same graph. The first question is, use the graph to determine the following. The EMF of the battery. So the EMF is the total voltage that the battery can supply. And so the moment that we have a current running through, so this is a resistor that has, it's a variable resistor, so we can change the resistance. Now, the moment that we have a current flowing, the energy that the cell provides has to be spent in the external current, but also because there's internal resistance, it's spent on the internal current as well. So the moment that we let a current flow, we start reading how much energy is spent on the external resistor. But if there's no current flowing, all of the energy is spent only, in other words, and then you'll see that the current will still be flowing, but there won't be any current going through here. So the voltmeter will actually be reading the voltage over the battery. So that if there was no current flowing, then the current would have been, so to get the EMF, we could just look at what is the current, what is the voltage, the voltmeter reading when there's no current. So there's zero current, no voltmeter reading. And so in here, unfortunately, this is not read. So what the student did is to calculate the gradient of the graph, which gives me a change of y over a change in x. Now, if we do that, the y value is current. So this is I over v. Now, I over v will give you, let's see, if I just write it like that. So we have that current is equal to voltage over resistance. So if I divide both sides with a v, I get I over v. This side will cancel, and so I over v will give you 1 over resistance. So not the correct answer there. Okay. What did the other student do? The student read it correctly off of the graph. You'll also see that when it's a 1-point question, it's probably a reading off the graph type question. Where can you read it off the graph? Or when there's no current, that is when our voltmeter reading will give us the EMF. Okay. Use the graph to calculate the internal resistance of the battery without using the calculation E is equal in your calculations. Okay, so again, the what do we have here? The student did change over y over change over v, that is the gradient, and he gets a gradient of negative 1 over 2, and so he takes that as the change in the internal, I don't know, by the way, I don't know, but let's go and have a look on here. So we know that our calculation should be this, I over r plus r. So if I just change this to be E is I times r plus I times r, and I solve for small r, I get I times r is equal, this is just normal voltage read on the voltmeter, so I get my EMF minus my my voltage read on the external circuit divided by and then here I'm just going to divide both sides with an I, my current, divided by my current. So it does look like I can do that. So for example, here is then the change in my voltage divided by my current. Just wondering why this isn't a change in current, but okay, no, this does seem that these methods should work. Okay, so in other words, change in voltage is then a change in X over a change in Y, or horizontal. So he is 100% correct in what he's doing here. Okay, so that will work, student 1. That you're taking the change in Y over change in V, that gives you the inverse relationship there, and this is why. Well, the reason why there is a decrease in voltage is because of the resistance. And so when we work out this, what is causing the change, it's definitely the internal resistance that's causing the change. And so very well done. The reason why he's getting this is exactly the same reason that I showed before, why the other student was incorrect in just taking y over v, in other words just the gradient, because that's 1 over r and it should have just been r. So or it is 1 over r, and so you swap it around. The gradient is taken the reciprocal of the gradient to get the correct answer. Okay, so very good response there by student 1. What did the other student do? Student 2, 1 over v is r over e, and 1.5. Okay, well, her v here, let's see if her method would have worked. 1 over v, oh, maybe it shouldn't be 1, it should be I over e. V is r over e. Let's see if she did it correctly. Okay, let's see. Just taking this equation of ours, can we get to the 1 over v is r over e? I don't think it's 1 over v. I think it might be r I over v instead of 1. Maybe she misread that. But so let's have a look. So in other words, what relationship can we get that looks similar to her response there? So again, if we look at this, we want to divide with the e. See, if I have e over I, e divided by r, I is r plus r, external resistance plus internal resistance. So I, okay, so let's not do this one, let's use this one. We've got E is equal to V plus IR. Let's see what we can do with that one. E is equal to V plus IR. Sorry, I just don't know that formula that she's using there. And so in here we would get it would still be E minus V over R is equal to I. Over 1. Okay, so all I did was take the V to that side, divide both sides with an R, And then, so this can maybe be true, that 1 over I is equal to R over the change in V. Okay, that can maybe be the closest thing that I can get to her equation. So 1 over V is equal R over E. Now that's the closest I can get. So I don't think with this she can get to the right answer. Okay, let's look at the next question. The next question is the resistance of the rheostat. That's a resistor that can change its resistance, is now increased. How will this change the voltmeter reading? Okay, so remember what a voltmeter does is it reads how much energy is spent in this resistor. So in other words, it reads the potential difference of the energy that electrons have when they come in and when they go out. So when a resistor is increased, it necessarily increases the voltage that is spent in that resistor. So for example, if I had two resistors in series, okay, then, and the total voltage over the two was 12 volts, okay, then they will share it. So let's say they were equal, then the one would have gotten 6 volts. Okay, in other words, every electron spent 6 joules per coulomb of energy there, and here 6 joules per coulomb of electrons was spent there. That's if they were equal. But the moment the one gets increased, then so in other words, this one has a higher, now more energy needs to be spent to get through this resistor in order to get that to that resistor. Now it's not the same in a parallel resistance. Okay, if I had two resistors in parallel, then here it works differently, is that the total amount of, so in a series we add up the voltage to get the total voltage. Here the total amount of volts, so if this was 12 volts, that's how much energy comes in and is spent in here and then comes out. But now each electron now goes, 1 coulomb of electrons goes this way, and another coulomb of electrons go this way. But the amount of energy that this coulomb has is the same. So this one will also get 12 volts, and this one will also get 12 volts. Okay, so both will have the same amount of energy. They will just have, here the whole current is coming through, and the whole current is coming through. In other words, all the electrons, all the coulombs. Here the current splits, and if they're equal, the current splits equally. But what happens now is if I increase this current, now, so not this resistance, now what's going to happen is that the current is going to decrease. And so fewer electrons will go in this direction, and more electrons will go in this direction, but the amount of energy that each electron has when he comes here is still the same. So in a parallel circuit, if I change the resistance, it doesn't change the amount of voltage at all. Okay, so here we must just decide now what is happening. If this thing is increasing, well, if it was the only resistance, okay, then nothing would change. If it was only him as resistor, and it looks like it's only him, but it's not. There's another resistor in the sequence, the internal resistance. And internal resistance is constant. Now the question is just, is it in parallel or in series with that internal resistance? And we can see it's in series, because the whole current comes through this one, and the whole current comes into the internal resistance. So increasing this resistance, which is what I think they said, increasing that will increase the potential difference. How will this change the voltmeter reading? It will increase the voltmeter reading. And let's just look at it in terms of this. So if we had my EMF is equal to my voltage plus my internal voltage, which is I times R. Well, how does that affect it? So, or we can write it like this: I times R plus R, like that as well. So by increasing this resistance, that one stays the same. What is happening, EMF stays the same, is that my current, this current is decreasing. So now it's a good question to understand, okay, if my current is decreasing, what's then happening to this relationship, I times R? Because one goes down and the other one goes up. Does that mean they stay the same? Well, it would stay the same if the one goes up and the other one goes down by the same ratio, because we're multiplying. So we can't just look at this relationship. So if resistance go up, the current goes down. Okay, if the current goes down, what is going to happen to this, the lost volts? Well, if the current goes down, there's less lost volts because my current is less, but this is constant. So this is constant. Let's write a constant like that. My voltage is not a constant. This I is not a constant, but R is a constant. So if this is going down, my current is decreasing, then my lost volts will be decreasing. And so if EMF is then constant, then this must increase to keep that constant EMF. Okay, so that's another way of looking and explaining it. Now I should have looked at the students' answers first to see if they got it. Let's see how they responded here. Well, this one is decreasing, and so that's not true. In this case, it will not decrease. A higher resistance uses more voltage or energy, using the external load to be causing the external load to be less. And so you've got the right start. A higher resistance uses more voltage or energy, and so that's in other words, the voltmeter will show a higher reading. So you had the right start there. See what this student said. Okay, so this student is on the right track. He's saying that yes, it increases. Then he says E is constant, I is decreasing, so then V external must be increasing. This is perfect, but you'll see here the answer requires 3 marks. So the 1 mark would go for your increasing here, but here, and because it says explain, you can't just say IR is decreasing. Why is it decreasing? So you would get 2 marks for this explanation, but explain, why is IR decreasing? And the reason why is because, and so basically if you were to put this in a nice sentence, you would say that when the external load is increased, the current is decreased. When the current is decreased, then exactly this, the lost volts, I times R, is decreased. And as a result, the external load reading is higher because there's less lost volts. Okay, but very good reasoning going on in 9.2.2 there. 4 identical cells, each with an EMF of 1.5 and an internal resistance of 0.25 ohm, are connected in series with each other, and the resistors is shown below. Write the potential difference across the cells when the switch is open. Okay, so in other words, if we were to measure the potential difference across the cells when the switch is open, okay, so it's obviously just 4 times 1.5, which is 6 volts. Let's see what the student did. 6 volts, perfect. Okay, next question. When the switch S is closed, the potential difference across the 4 ohm resistor is 2 volts. Okay, across the 4 ohm resistor, okay, that one is 2 volts. Calculate the current in the circuit. Okay, so we know let's quickly see. They give us the voltage over there. We have the resistance. Okay, so since the whole current is passing through the 4 ohm, I can just use everything I know about the 4 ohm to get the total current. So let's see if that's what the student did. The student didn't go any she must have. I don't think this is correct. 932. Okay, like the current in the circuit. Let's just see what this student did. Yeah, this is it. So you just use the information that you have about this one, because the reason why this one is not working, this is because the R represents the total current of the external circuit. Not current, I lie, sorry, the resistance. This is the total external resistance, and it's not just 4. So that's why this one doesn't work. But this is perfect. I know that the whole current is passing through 4. So if I wanted to get the total current, if I know everything about the 4 ohm resistance, and I do, I know his voltmeter reading and I know his resistance, and I know that the total current is coming through here. Why do I say the total current? Because there's no other way. There's no route around it. There's no another branch. And so this is indeed correct. Okay, so 9.2, calculate Rx. So let's look at what this student did. First of all, he's doing this correct. So here is his expression for any circuit that has internal resistance. He substitutes his 6 volt EMF, his 0.5. Then for his external resistance, he's doing this. He's saying the resistance of the parallel group plus the 4. Why plus? Because the parallel group and the 4 is in series with each other. In other words, the total current comes into 4 and the total current comes to the parallel resistance. It does split up then, but if I consider this as a whole, the total current will come through here and then come back there. And so then he calculates, so 0.5 divided by that is 12. 4 times 0.5 is then 1. So the 1 gets subtracted from the 12 is 13. The 4 gets subtracted from there is 9. 11. 4 minus 7. That's perfect, sorry. And so this is the resistance of the parallel branch. And so now we know that 1 over the parallel branch is equal to 1 over the parallel grouping is equal to 1 over the resistance in branch 1 plus 1 over the resistance in branch 2, and then he just substituted and he solved. So he gets 1 over 7 is equal to 1 over 14 plus 1 over R, and I don't know if he did this by inspection or if he did the calculation, but this is indeed 100% correct. For the other student worked out 4 over 2, so yes, perfect. You got the current that goes into 4 is 0.5 amperes. That's correct. So that was supposed to be the previous question. Now you get 4 divided by 14. Okay, I don't know where this 4 comes from, and this is wrong. 4 divided by 2 is not 0.5. I don't know where this 4 comes from. What is this 4? 1.2. Where does the 1.2 come from? No. I'm afraid, student, I can't figure out what you're doing here. Your current is equal to your voltage divided by your resistance. 2. So I don't know. Well, this is obviously wrong. How you're getting this, I'm not sure. And again, this is okay. So you are saying here that your voltage is 4. I suspect you're saying that your voltage, because this is true, that the current, the voltage is split up. If this one gets 2 volts, then this one should get 4 volts. But that's only if there wasn't already voltage being used. So the thing is, yes, there's 6 volts supplied, and this one gets 2 volts. But in order to do what you did here, where you took the 4, you first had to then go and work out. So in other words, if you had the current, just to do what you are doing here. So in the first step, we worked out the current is 0.5. You worked it out wrong now, but don't worry. You could have used your answer. So the current is 0.5. So you want to split up the voltage, and so you have to split it up over all the groupings of resistance. So this one we know gets 2 volts. Now we want to know how much does this one get. Well, that one current is equal to volts over resistance, and so here we want to work out how many volts are lost, in a sense, on this. We know that the internal resistance is 1 because it's 0.25 per resistor. There's 4 resistors. We know now that the current is 0.5, and so my voltage lost is then just 0.5. Okay, so that is the amount of energy spent in the battery. There's 2 volts of energy per coulomb spent in this 4 ohm resistance. And so how much is left? Well, there was 6 volts in total, and so 2.5 has been spent, so there's 3.5 volts that is spent across here. So that gives us the ability to work out then what is the current in here, and I think that's what you were doing. So in my 14 ohm, and so I know over this whole group there is 3.5 volts spent for this whole parallel group, and because it splits up, it's spent here and there at the same amount. The only thing I don't know about this one, so I know this one has 3.5 volts, but I don't know what's his current. I know what the whole current is coming from here, and I know it splits up, but I don't know in what ratio. So if I can work out what the current in this one is, I can just subtract it from the current, because the whole current splits in 2. And if I can know what big of a portion goes this way, I can work out that way. So that's what I think you were doing. And I do think that's what you were doing. And so my voltage over my resistance, my voltage is then 14, my resistance, my voltage is 3.5, 5, and my resistance is 14, and that gives you 0.25. Okay, now if I knew that my whole current was 0.5, and the current going in this way is 0.5, then I know that the current going into Rx is also 0.25. And so I know his voltage is 3.5, because they must have the same voltage. In parallel branches we have the same voltage, divided by the unknown resistance. And we see it's the exact same expression, so this just leads to Rx is equal to 14, I mean. Oh. Okay, So I think that's what I'm seeing you doing here. So you were on the right track here, because you are subtracting the current that is in 4, and you're subtracting the current that you found in resistance 14. The only thing is, you are misunderstanding current, because when current passes through 4, it's the same current that it's, consider a river. When the current or the strength of that river passes through the resistance, it's still the whole river that comes out on the other side. It's only here where the river splits into 2 legs, and so it's only here where we would have subtracted. So you were right in subtracting the 0.3, but you were wrong in subtracting the 0.5. And so nevertheless, you then got that, and you used that over the 4. You still used the 4, which again you misunderstood the voltage. Yes, 2 volts are spent here, and so you should have used the 2 volts there divided by the 4 to get this current here. I don't know what you did there, and but yes, I think I've explained more than enough. Okay, so very nice question, I must say. I like it.